Yesterday, when we left off, we were talking about finding the nth term of an arithmetic sequence and going back and forth between the explicit and recursive formulas for an arithmetic sequence. Oops. So today, yeah, you're right. Today we're going to talk about the sum of an arithmetic sequence, or in other words, an arithmetic series. Arithmetic sequences, we talked a lot about those yesterday. We have the nth term formula. Let's just go ahead and review really quickly here. So arithmetic sequences are any sequence where any two consecutive terms are separated by a constant value. And so the nth term of an arithmetic sequence is just the first term plus n minus 1 times d. We know that d is that common difference, right? And so that's the explicit formula for the nth term of an arithmetic sequence. We can also define it, an arithmetic sequence, recursively, right? And say that the first term, a1, is just equal to some value, it doesn't matter what it is, and then every subsequent term, a to the n, is going to be equal to a to the n minus 1 plus d. So this is the explicit nth term definition, this is the recursive definition. Right? We can go back and forth between those two if necessary. Okay? Now, what we're going to start talking about today are, instead of we're going to take these arithmetic sequences and we're going to add up the first n terms of those sequences. And so we're going to start talking about arithmetic series. Because we know a series, right, is the sum of a sequence. So if we want to have the sum of the first n terms, or all of the terms of any type of sequence, we call that a series. And because it's an arithmetic sequence, it's an arithmetic series. So the question is, can we come up with a formula that gives us the sum of the first n terms of that series? Okay. So first of all, let's say we have an arithmetic series, which I'm just going to call S sub n, which is the series, which is just the sum of the first n terms, right, of the series, all the way out to a sub n, right? We're adding those ones up, right? And so the thing about this, though, is that we could actually write all of these in terms of a sub 1, right? Because these are all just certain distances beyond the first term, which is a sub 1. And that distance, we know, if this is an arithmetic series, we call d. That's the common difference, right? So I'm going to go ahead here and I'm going to write these all in terms of d. So a sub 1 plus a sub 1 plus d, all right? That would be a sub 2. A sub 3 would be a sub 1 plus 2d, right? All the way out to a sub n, which would be a sub 1 plus, and of course I didn't give myself enough room here. Just going to open up a little bit of room here. So we have a sub 1 plus 2d, right, for the third term. And then following that logic through, the nth term would be a sub 1 plus n minus 1 d, right? Which makes sense because that's just the nth term formula, right? So that's where we end up right there, right? And so what we get here is we end up adding up, if we reorganize this, right, we take all the a sub 1s and, using the commutative property of addition, add them all together. We're adding a sub 1 together n times, right? And then how many times are we adding d together? Well, we have 1d, then we have 2d's, and then we have 3d's, all the way to n minus 1. So we end up having d times, right, 1 plus 2 plus dot, 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 all the way out to n minus 1. Right? And that's a sequence that we know the formula for, don't we? right? Does anyone remember that was one of those formulas that we were given from the other day. So this first one we have n, and then first of all, adding a sub 1 together n times is the same as n times a sub 1. And then over here we have d times 1 plus 2 plus 3 plus 4 all the way to n minus 1, right? We're going to use our formula, which was what? What was our formula? If we go back, we find the formula for the first n terms of this particular sequence, 1 plus 2 plus 3, but we want the first n minus 1 term, so we have to have one less than that. Normally it's, so it's n times n plus 1 over 2 was the formula. So I'll write it up here in the top. N times n plus 1 over 2 is the formula for the sum of the first n terms of this sequence, but we only want the first n minus 1 term, so we're going to plug in n minus 1 right there. And then we're going to plug in n minus 1 into n plus 1, and n minus 1 plus 1 is just n over 2, right? And so by substituting in that formula, now we have a closed formula. And by closed, I mean there's no more dot, dot, dots here, right? I got rid of all my dot, dot, dots. It's just a nice closed formula now. And so we're almost there. We have a formula. We just want to clean this up and make it look a little bit nicer, right? And so if we go ahead and we do that, what I'm going to do here is essentially I'm just going to go ahead and I'm going to factor out, n minus 2 is a factor here and n is a factor here. So I'm going to go ahead and factor out n minus 2. Sorry, n divided by 2, I should say. If I do that, what happens when I factor out n over 2 from n sub a1? What am I left with? The n goes, but what else do I have there?
a1 over 2.
Yeah, a sub 1. What happens if I multiply back through by 1/2? Should it be 2a sub 1? So that they cancel on the one when we go back through. And then plus d times n minus 1 times n. All right, so the n over 2 goes out there. And so, oops, what did I not do there? I was going to say it doesn't look right. That n should have come out. I forgot to, that was gone. Now, we're getting really close. So that's one of the formulas we can use there. So this is one of the formulas. And this formula is really useful if you know a sub 1, you know d, and you know n, and you want to find the sum of the first n terms of an arithmetic sequence, and you know all three of those things, then that's a good formula to use. But there's other formulas we can use as well. If we say this is s sub n is equal to n over 2, and we do a sub 1 plus a sub 1, right? It's supposed to saying 2a sub 1. What is this right here? Does that look familiar? What do we think? A sub 1 plus d times n minus 1, what is that? That's isn't that the nth term? Right, so this whole thing right here is just a sub n. So this is another, so that gives us another version of the formula here, which is useful if you know the first and nth terms and you know what n is, of course. Right, so we're going to use the formula that's going to go along with the data that we have about the particular sequence, right? So there we go. That is the sum of the first n terms of an arithmetic sequence. In terms of intuitiveness, this last one I really like, because think about what we're doing here. We know that there's a common difference between all these terms. So if I add up the first term, and then I add up the first and the nth term and divide it by 2, what is that giving me? The first and the nth term divided by 2 is just the what of the first and the nth term? The average. So that's the average, and in an arithmetic sequence, everything is spaced out very evenly, right? So this part is just the average of all the terms, essentially. If they're evenly spaced, then the average of the first term and the last term is going to be the same as the average of all the terms. If I just added up all the terms between a1 and a sub n, and then took the average of that, it should be the same as just the first and the last term divided by 2, because they're evenly spaced, because it's an arithmetic series. So this is just the average value of all of the terms of this arithmetic sequence. And if I multiply that by n, I take the average value by the average value per term and multiply by the number of terms. There's your sum right there. And so that makes sense. This formula makes sense intuitively, even if you didn't see the proof, the algebraic proof, right? All right. So for example, let's say have the arithmetic sequence a sub n is equal to 3n plus 5. We actually, the other day, we proved that one is an arithmetic sequence, and we could do that if we want to. Find the sum of the first terms of the first n terms. So go ahead and use what you know with that formula that we just developed and find the sum of the first n terms of that arithmetic sequence. Okay, so the first n terms of the sequence, we know the nth term is this. So I already have the nth term, right? I have a formula for the nth term, right? So that's important to know. And using our formula, we figure out that a sub 1 is going to be what? It's going to be 3 times 1 plus 5, which is 8. So I have a sub n and a sub 1 right away. Could I figure out d? I could pretty easily, right? Just by finding a sub 2 and figuring out the amount that they are apart. And we know, based on what we saw before, that this is an arithmetic sequence, so that difference is going to be the same for every single term. But I already have a sub n and a sub 1. So the formula that involved a sub n and a sub 1 is probably the one that I want to use instead of the formula that involves a sub 1 and d. I could find d, but why not just use the information at hand? So I'm going to use the sum formula, which involves a sub 1 and a sub n. So the sum of the first 10 terms is going to be n times a sub 1, which is 8, plus 3n plus 5, which is a sub n, all over 2. Right? And so we could, of course, go ahead and simplify that if we wanted to. And we'd get n times 3n plus 13 over 2. And then if we wanted to go ahead and distribute the n, we'd get 3n squared plus 13n over 2. And so if we just plug in the number of terms, that will give us the sum of the first n terms of that arithmetic sequence. Now, given the explicit formula of the arithmetic sequence for the nth term, if we're just given the terms of the sequence, so find the sum of 60 plus 64 plus 68 all the way to 120. Right? So find the sum of all of those terms. Now you can see the pattern, right? You can see that's the first certain number of terms of some arithmetic sequence. And you're going to have to find the information you need to know to use that formula that we just had there. So give that a shot. Okay, so for this one right here, the first term is 60, the last term is the nth term, I should say, is 120. So we know the first and the last term, so we're probably going to use the formula. The sum of the first n terms is equal to n times a sub 1 plus a sub n over 2. We know a sub 1, we know a sub n. We've got to figure out what n is equal to, though, don't we? How can we figure out what n is equal to? What do you think, guys? My hint is always go back to the nth term formula. Plug in what you know into the nth term formula and solve for what you don't have, even if you don't care what the nth term is, because you already know it. So let's say that the 120th term, right, is going to be equal to, so that's the nth term. I don't know what that is. I don't know what n is, right? It's going to be equal to a sub 1, which is 60, plus n minus 1 times d. What's d? So if we just plug all of the information that we know into the nth term formula, we can solve for what we don't, assuming we know enough information, right? So we'll end up getting that 60 is equal to 4n minus 4. And so when we end up solving for n, we get 64 divided by 4, which is 16. So that means there's 16 total terms. And so for our particular sequence, s sub 16 will be equal to 16 times 60 plus 120 over 2, right? And And that will end up giving us 16 times 180 divided by 2, which is 1440. So the sum of those terms is 1,440. Okay. All right, let's look at a word problem. Knowledge of what's... All right, so we have a word problem here we're going to take a look at. This is going to involve, to solve this, it's going to involve using what you know about arithmetic series. So we have this, we have the diagram where we have the picture of what's going on here. But anyways, they're making a ceramic floor in the shape of a trapezoid, 20 feet wide at the base and 10 feet wide at the top. The tiles are 12 by 12. And they're placed so that each successive row contains one less tile than the preceding row. So there's 10 at the top and 20 at the bottom. Question is, how many tiles will you need? Use what you know about arithmetic sequences to solve this problem. In other words, don't just brute force method this one. Actually use the arithmetic sequence stuff that we just learned to make this a much less calculation intensive problem to solve. So in this case right here, creating floor design, we have 10 tiles on the top and 20 tiles on the bottom. So 20 down here, right? And we have 10 tiles across the top there. And then each one is one less. Then this one has 11. This one has, or it has one more, I should say. This one has 12. And so if I want to add them all up, I'm essentially adding up 10 plus 11 plus 12, all the way to 20, right? So that's just an arithmetic sequence. D is 1, first term is 10, last term is 20. And the question is how many layers are there? You could count them, right? That would not be unreasonable, but you could also plug it into the nth term formula. The last term is 20, right? Whoops. 20, and the first term is 10 plus n minus 1 times d, which is 1. We'll end up getting 10 is equal to n minus 1, and so n is equal to 11. There are 11 layers, and of course I could count that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 layers, so that works out. So if n is 11, then the sum, the total number of tiles that they're going to need is going to be 11 times 20 plus 10 over 2. So 30 plus 11 is going to be 330 divided by 2 will be 165. So they're going to need 165 tiles to complete this particular project right here. Alrighty, so that's it for arithmetic sequences. So why don't we take a quick break, and when we come back we'll start talking about geometric sequences. Let's talk about geometric series now, or sequences to start, and then we'll talk about series. Right, so what is a geometric sequence? A geometric sequence is a sequence where any two consecutive terms have the same ratio. Have a constant ratio, right? So instead of having a constant difference, right, in the case of a arithmetic sequence, any two consecutive terms have a constant difference. These have a constant ratio, which means that a sub n divided by a sub n minus 1, so if we take the ratio of the nth term and the n minus 1th term, that's equal to some fixed ratio, which we'll just call r for now. And that is called the common ratio instead of the common difference. Right? And so recursively, I could say the nth term is equal to r times a sub n minus 1, right? So that's and then of course the first term is just whatever it is. So a sub 1 is equal to just a, and a sub n is equal to r times a sub n minus 1. So this is the recursive definition of a geometric sequence, right? formulas that we can use for a geometric sequence. Sometimes also called a geometric progression. For whatever reason, they use that terminology at times. So called either a geometric sequence or a geometric progression, right? So let's go ahead and so in this first example here, let's look at the sequence 2, 6, 18, 54, 162, and so on. Is this geometric? And if so, find the common difference. Okay, go ahead and, is it geometric? Confirm that numerically or algebraically. And then if it is, find the common, not the common difference, the common ratio, sorry. Find the common ratio. All right, so what is, the first term is a sub 1, right? And what's the ratio here? Well, 6 to 2 is equal to 3, right? 18 over 6 equals 3. 54 over 18 equals 3. And 162 over 54 also equals 3. So they all have the same common ratio, therefore it's geometric. And the common ratio, my R value, is 3. So a sub 1 is 2, and my R value is 3. All right, so what if, instead of giving you give you an explicit formula for a sequence. So the nth term of this sequence is 2 to the negative n, right? Is it geometric? First of all, so same question, is it geometric? If so, find the common ratio. So this is going to involve, especially the first part, it's going to involve a little bit of algebra, a little bit of algebraic rules. So go ahead and give that a shot. All right, so in this case, is it geometric? So S sub n is equal to 2 to the negative n. The nth term is 2 to the negative n. The n minus 1th term is going to be equal to 2 to the negative n minus 1, right? If we plug in n minus 1 instead of just n. So let's figure out, is that ratio going to be constant? So S sub n divided by S sub n minus 1 is going to be equal to 2 to the negative n over 2 to the negative n minus 1. Now, what do our exponent rules tell us that we do here? What do we do when we divide exponential expressions that have the same base? We do what? We don't do any dropping. What do we do with the exponents when we divide exponential expressions at the same base? Yeah, we're going to go ahead and do 2 to the negative n minus negative, there's a lot of negatives here, n minus 1, right? So we subtract the bottom of the top. And so when I reconcile all these ridiculous negative signs here, negative n minus negative n, those are going to cancel. And then we have 1, 2, 3 negative signs, meaning that's going to be a negative 1 right there. Right, so the n's cancel. We're just left with 2 to the negative 1, which is the same as 1/2, right? So it is geometric. And what's my common ratio? 1/2, right? Because no matter which two terms, which two consecutive terms I pick, because this is general, right? This could be anything, right? These could be any two terms here. No matter which two I pick, if I divide them, I get a constant ratio of 1/2, right? So I've proven that. And so I have my common ratio there. Okay, so if we go ahead here and we think about this, let's look at a specific series here. If I have the series, let's say 2 to the n, just a really simple one. So let's say that we have some sequence a sub n, which is just 2 to the n, right? So it's going to be, the first one is going to be 2 to the 1, right? And then the next one's going to be 2 to the 2, the next one's going to be 2 to the 3, the next one's going to be 2 to the 4, and so forth, right? Right? And so my a sub 1 is equal to 2, right? And every subsequent one is just some higher power of 2. Actually, let's say that instead it's going to be 3 times 2 to the n. Now, let's just leave it like this. I take that back. All right. So a sub 1 is 2, and every subsequent term is 2 to the 2, 2 to the 3. We multiply by 2 a certain number of times. So what we're seeing here, if I rewrite this, I'll get, right, 2, and I'm going to write this like so. 2 times 2 to the 1, 2 times 2 to the 2, 2 times 2 to the 3, right? If we write this in terms of like a sub 1, and then a sub 1 being multiplied by 2 to the 1, being multiplied by 2 to the 2, being multiplied by 2 to the 3, right? It sort of follows that the nth term is going to be 2 times 2 to the n, right? And if this is my a sub 1, then in general, we could say that for a geometric series, if you want to get an explicit formula for the nth term of a geometric series, sort of drawing a conclusion from this situation, the nth term, a sub n, is just going to be a sub 1, my initial value, times r to the, well actually if we think about this, sorry, so this is the first term and second term, third term, fourth term, so this is n minus 1, this is n minus 1, this is n minus 1, so really, I sort of made a mistake here, this should be 2 times 2 to the n minus 1, it's always multiplying by 2 to the 1 less power than the number of the term that it is. So it's going to be r to the n minus 1. Right? So a sub 1 times r to the n minus 1. So we're multiplying by that common ratio n minus 1 times, right? That's the same as taking r to the n minus 1. So a sub 1 has to get multiplied by the common ratio n minus 1 times, and that will give me a to the n. Right? And so this is my formula for the nth term. That's my explicit formula for the nth term of a geometric series. Right? So now we have the explicit, we had the recursive formula from earlier, and now we have the explicit formula as well for that situation. Formula in an example here. Let's say I have the sequence 10, 9, 81 tenths, 729 over 100. So, part A, find the nth term. Find the ninth term. Find a recursive formula. And yeah, so go ahead, find the nth term. In other words, find the explicit formula for the nth term of this particular sequence, find the ninth term of the sequence, and then find a recursive formula for the sequence as well. So we want to find the nth term first. So first of all, a sub 1 is equal to 10. What is the common ratio that we multiply by each time? What do we multiply each time? What's my r? 9 tenths, yeah. Because if I multiply 10 by 9 tenths, I get 9. If I multiply that by 9 tenths, I get 81 tenths. And if I multiply that by 9 tenths, I get 729 over 100. So yeah, my common ratio is 9 tenths. So a sub n is going to be equal to 10 times 9 tenths to the n minus 1, right? For the nth term. Make sense so far? And that works for the first, and the reason it works for the first term, right, is because if I plug in 1 for n, I get 9 tenths to the 0, which is just 1, and we get the first term, 10. We haven't multiplied by the first term. We shouldn't have multiplied by the common ratio at all, right? Okay, so that's a sub n, that's the nth term. The ninth term, a sub 9, it's going to be a very large number, as we can imagine, or they're going to have very large numbers in there. It's going to be 10 times 9/10 to the 8, which, if we multiply that out, is going to be 430,467 to 10 all over 10 to the 8th. And I should have parentheses around this to get the whole thing as being raised to that. And 10 to the 8th is 8 zeros.
Did you multiply the 12 by the 10 already?
Oh, no, I didn't. I got to put another 0 there for the 10. So, that's a pretty interesting number, right? Not necessarily an enormous number because it's a ratio, but the numerator and denominator are quite large. And the recursive formula for this whole thing is going to be, well, a sub 1 is equal to 10, and a sub n is going to be equal to a sub n minus 1 times 9/10. So that's the recursive formula. So we have the explicit formula, the recursive formula, and the ninth term for this particular geometric sequence. Okay, so naturally the next question, based on what we've been talking about before, is what happens when I add up the first n terms of a geometric sequence, right? So we have a geometric sequence. So we're gonna start talking about geometric series now. Right, so if I have a geometric sequence, let's say S sub n, which is equal to, a geometric series, which is going to be a sub 1 plus a sub 2 times r plus a sub 3, a sub 1 times r plus a sub 1 times r squared plus a sub n times r to the n minus 1, right? Sorry, a sub 1, my bad, I keep screwing it up. A sub 1 times r to the n minus 1 times, that's the nth term formula, right? What does that end up adding up to? Can we, just like we have a formula for the sum of an arithmetic series, can we find the sum of a geometric sequence? Right, so we're going to use a little trick here. The first thing I'm going to do is I'm going to go ahead, I'm going to multiply both sides of this equation by r. If I get that, I'll get a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed, right, all the way up to a sub 1 times r to the n, right, because r to the n minus 1 times r, right, is going to be just r to the n. Does that make sense? All right, so we've done that. And so now I'm going to go ahead and I'm going to subtract the first equation from that equation. Actually, is that the order that I want to do? So anyways, I'm subtracting this equation from this equation. So if I continue on here, minus a sub 1 minus a sub 1r minus a sub 1 r squared and so on, all the way to up to minus a sub 1 to r to the n minus 1. So if I subtract that, what am I going to be left with, right? If I subtract that, on the bottom here, I'm subtracting a sub 1. There is no a sub 1 term by itself in this particular one, so this is still going to be here. Right? But then these are going to cancel. These are going to cancel. Right? And it's going to cancel all the way out to here, because there's going to be an r to the n minus 1 in this mix here, right? It's going to be the term before this one. And so that's going to cancel with that, and we're going to be the only term in this sequence right here that we don't have on the top here is this one right here, a sub 1 r to the n. So we'll still have a sub 1 r to the n. Right? So once again, this is a little trick that you use sometimes, subtracting one series from another series to eliminate everything except for a finite number of terms. And now I want to know what I want to have like a nice formula for s sub n, right? So I can factor out s sub n right there. Then over here I can factor out a sub 1 too, and I'll be left with r sub n minus 1 if I do that, right? And so I'll end up getting s sub n, the sum of this series is going to be a sub 1 times r to the n minus 1 all over r minus 1. Okay? Okay, so that is the formula for the sum of a geometric sequence. Some people also write it in a different form. They factor out a negative 1 from the top and the bottom, and if you do that, you get a sub 1 times 1 minus r to the n over 1 minus r. So that's another possibility that works too. Right? So either it's the same expression. It's just put in a different order more or less. So in either case, if I want to get the sum of the first n terms of a geometric series, I can use this formula right here. Okay? So if I said find the sum of the first 10 terms of the sequence, a sub n is equal to 1/2 to the n. So find the sum of the first 10 terms of that sequence. Want to find the sum of the first n terms of the sequence, keeping in mind that we just determined that s sub n is equal to a sub n times 1 minus r to the n over, sorry, that's a sub 1. Apologize there. A sub 1 times 1 minus r to the n over 1 minus r. So we need to know a sub 1 and r and n to be able to use this formula. So n, of course, is 10. A sub 1 is just going to be equal to 1/2 to the 1, which is just 1/2. And our ratio is what? Yeah, the ratio is also 1/2. The first term is 1/2, and the ratio is 1/2, because every subsequent one is just going to be multiplied by 1/2. So we'll get s sub 10, in this case, will be equal to 1/2 times 1 minus 1/2 to the 10th over 1 minus 1/2. Right? And so we'll end up with 1/2 times 1 minus 2 to the 10th is a big number, right? It's 1024, so 1 over 1024 over 1/2. Right, the 1/2s are going to cancel, aren't they? So we'll end up with 1 minus 1 over 1024, which is going to be 1023 over 1024, which is about equal to 0.999 023. So very close to 1. Very close to 1. All right. Let's just get so we don't lose any skill with that. So use a graphing utility. Your graphing calculator, that is, to find the sum of the first 15 terms of the sequence 1/3 to the n. Or let's say of b to the n equals that. Okay? So find the sum of the first 15 terms. Use your graphing calculator, meaning we showed you how to use the sum and sequence functions. So use the sum and sequence functions in your calculator to find the sum of the first 15 terms of that particular sequence. Okay, so to use your calculator to find the sum of the first 15 terms of this sequence right here, we're going to use the following command in your calculator, which is sum of sequence, right? In the sequence function, we're going to put in the sequence definition first, which is 1/3 to the n, right? And then we need to put in our independent variable n, and then we want to go from the first term to the 15th term, right? And then we want to increment 1 each time, which means we're not skipping from the first term to the third term to the fifth term. We're going 1, 2, 3, 4, 5, all the way to 15. And then close both parentheses. And this should give you, so you'll get 0.4 and then 69652. So another one, that's really a number that's really close to half, but not quite half. Just as a reminder, the sum and the sequence functions are both from the second stat menu. You can find both of those. Sum is under OPS. Sorry, sum is under math, and sequence is under OPS. So math will give you sum, OPS to get sequence. All right, so first you do second stat, and then if you want sum, you go to math. You want sequence, you go to OPS. That's where these commands come from, right? And so these are useful commands. All right, so that we're going to call it quits a little bit early today because we're done with the material that I wanted to go over today. And so your homework for tonight will be, so this is your homework for tonight. The first one here is from the old handout that I gave you yesterday. And this page 830 is from the new handout that I will be emailing out to everyone today. And I had been telling everyone that I was going to tell you the date of the final, so I'm tentatively, and I'm going to wait for people's feedback to confirm this, but I'm going to tentatively say that the final for pre-cal, for those people who have not taken Honors Algebra 2 but just took regular Algebra 2 and need the final to be able to move on to Calculus, I will be giving that on Thursday, August 21st at 10 a.m. in room 28, my room. So Thursday on 8/21 at 10 a.m. in room 28. If that is not going to work for anyone, and I will email that out as well, but if that is not going to work for anyone, please speak now or forever hold your peace. We can change that. It's flexible, but that's what I'm proposing. And if that works for everyone, great. If not, we can find a better time that'll work for everyone. So please get back to me immediately if that is not going to work. And if you don't have to take the final, then after tomorrow you will be done, and you can just, if you want to continue studying more topics that we didn't get to, you can certainly do that, or otherwise you're ready to go for calculus when we start on the 2nd of September. All right, everyone have a great day.